Okay, here's the actual lecture for week 8. Welcome back. One class to go after this. If you didn't read the Moodle, you may not know that I'm just going to give a quiz for this week and a quiz for next week. I'm not going to give a cumulative final exam, and then all the quizzes are going to be equal value along with the other two things I can grade by. I don't have a lot to grade by this term. Is attendance, whether you actually went into Moodle, did your stuff, and submitted a quiz, the grades of the quiz, and any extra credit you've gotten. This week I want to scratch the surface on transformers. I may also talk a little bit about three-phase, probably in a second video, depending on how quickly this one goes. So transformers are something that we actually get to touch and feel and use every day as electricians. Transformers, we are working on the secondary side of a transformer on almost every service we work on. A transformer is just two coils, or at least two coils, sometimes more than two coils if you're working with a multi-coil transformer, a three-phase transformer, or even a two-phase transformer. Things such do exist. They're just coils, and what they are is they use the properties of inductance. There's a thing called Lenz's law and some other things you need to know about coils that I'm not going to teach. But I'm going to teach you the basics. They use the property that when an alternating current is pushed through a conductor, it expands and contracts a magnetic field. And that magnetic field, if it crosses another conductor, induces a voltage on that conductor. And if there's a closed path for current to flow, it will push current through. So if I have two coils, I'm going to draw a model of these. Here's my first coil, and here's my second coil. So these are just the wires, right? I'm just drawing wires. And we'll often draw a transformer to look like this. Now in the real world, these two coils may be on a common core. They're probably on a common core. They can either be on a single core and wrapped together, all insulated so they don't actually make any electrical connections, or they may be on a big square-shaped core. Please do read chapter 28, unit 28 in the Delmar book. It has a lot of good information on coils that I'm not going to cover today. I'm going to give you just the very, very basics. But these are two coils that share, if not a common core, a common space. And they are built so that when one has a current flowing through it and its magnetic field expands and contracts, that magnetic field crosses over against the wires in the other one. And depending on how these are built, we can change a voltage of a system from any voltage to any other voltage, theoretically. Now, the transformers I'm going to draw, I'm going to say have perfect impedance. They have zero impedance. The wires that they're built with are absolutely resistance-free, which in the real world doesn't work, but for the purposes of our models and understanding the theory of transformers, it's a good thing to do. So when I draw these transformers, I usually draw left to right, just because that's the way I'm oriented as somebody from the Western Hemisphere. We read from left to right. So I'm going to call this the primary coil, and I'm going to call that the secondary. And all that means, really, is that I'm putting power on the primary. I'm actually going to hook up a voltage to this somehow, and I'm going to use the secondary for some other voltage system. Might even be the same voltage. You can have a transformer that doesn't change the voltage at all, but just gives a bit of separation between the two. There are no electrical connections in a standard transformer. If it is if it's an auto transformer is what they call it, there may be a connection between the neutrals. But the way we're going to talk about them, there's only the connection of those magnetic lines of flux crossing conductors and inducing a voltage. There's no actual physical connection. So they'll call that an isolation transformer. And that's what I was talking about when I talked about a transformer may not change the voltage. That's the main use they're for. Sometimes they're just there for isolation. And that's something we can get into later as to why you would want that. But so we're going to call the power side that I put the power on the primary. We're going to call the side I take power from the secondary. And so thinking of it in that orientation, often you'll see them drawn like this. I'm going to figure out what my voltage is from one to the other by a couple of basic standard rules about transformers. So the first rule is power in equals power out. I can't create, destroy, or otherwise alter energy. I can only changes form, or something like this. Second law of thermodynamics, if you want to look it up. I can't ever make more energy than I had, and I can't destroy energy either. Energy is a constant, and so you know, we say that we dissipate power. We're just creating heat, so we've turned electrical energy into heat energy. When we use energy, electrical energy, to cause something to rotate, we've changed electrical energy into mechanical energy. So we haven't gotten rid of it, we've just changed it. So in this case, whatever the power is on the primary, it's going to be the power on the secondary. So let's say, for example, I hook up 200 volts AC. Got to be AC because DC won't work, right? Got to be AC, and let's say I'm at my 60 hertz. I'm going to hook up 200 volts of power at my primary. I'm going to get some sort of voltage at the secondary. And I can connect it to a load, and it will push electrons through that load. Now, how much voltage am I going to get at the secondary? Well, that all depends on the number of turns in both the primary and the secondary. And when I say the number of turns, I mean the actual physical number of windings on this side and on this side. And the ratio of those windings ends up being the same as the ratio of the voltage. We call that the N ratio for number of turns. You can also call it the turns ratio. You can also call it the voltage ratio. And that is simply from what voltage do I have here to what voltage do I have here. And it's exactly the same as how many turns do I have here compared to how many turns I have here. So let's say this 200 volt primary had 20 turns in it. So if I physically counted the number of times that wire wraps around the core, it'd be 20 times. That's a really small number. Obviously, a real transformer is going to have a lot more than that. But let's say it's 20 turns on this one. And let's say over here, I only have 10 turns on this guy. So if I had 200 volts here, I don't know what voltage I have here, except that I know that my turns ratio is 20 to 10, which is the same as 2 to 1, right? 20 to 10 is 2 to 1. If I have twice the turns that I have here as I have here, I'm going to have twice the voltage here as I have here. So if it's 2 to 1, I have 200 volts, and we do a little bit of quick math, and I'm going to have 100 volts between here and here. I have 100 volts induced upon this coil by the fact of this guy's electromagnetic force. The electromagnetic field expanding and contracting across these wires will induce 100 volts on this. And so this is just like I had a 100 volt source. In fact, every AC source that you guys work on in houses and such, it's just coming off the secondary of a transformer up on the pole. Assuming you're working on a house, a residential electrician. You know, same thing for industrial and commercial. There's either a ground mount or a pole mount or a vault mount transformer somewhere, and the power coming to your service is the secondary. That's all it is. It's not magic. Now, we may ground that. It may be grounded here. All sorts of code questions touching on that. None of that matters for theory and what we're doing right now, though. So, that's my N ratio. On this particular one, my N ratio is 2 to 1, or 20 to 10, or 2,000 to 1,000. Doesn't matter as long as the ratio is the same. As long as this number is twice this number, I'm always going to have twice the voltages there that I have here. So we call this a step-down transformer, the way it's hooked up. Now, if I took this exact same transformer, instead of putting a load on this side, I put power on this side, and instead of putting power on this side, I put a load, it would be a step-up transformer, because I have fewer turns here than here. So if I put, say, 100 volts of power on this guy, and put a load over here, I'd get my 200 volts. It would step 100 up to 200. If I put 200 volts on here, I'd get 400 here. If I put 2,000 volts here, I'd get 4,000 here. If I put 2,000 volts on the primary for a 2 to 1 transformer, I'd get 1,000 volts on the secondary. And whichever side I put the power on is the side I put the primary, but I'm using this example as this has more turns than this one as a step-down transformer. So here's the other cool thing. Let's go ahead and put some other numbers on this and talk about current flowing in these wires and in these coils. Now, you guys may recognize each one of those on either side of that core, the secondary and the primary, as essentially being series circuits. There's one current path, right? The voltage is developed here, the current goes around through. There's one current path. Same thing here. I've got a power source, one current path through the coil, the way I've drawn them. So they're both series circuits. So we know that the current anywhere in this circuit is going to be the same as anywhere else on this circuit. And we know the current anywhere on this circuit will be the same. Series circuits, voltage divider. We don't have any dividers. We only have one load. We only have this coil is essentially the load on this guy. So we're going to have all of our voltage drop here. And the same thing here, this guy's going to have all of its voltage drop. But mostly important about current, because what do we know about the current? Let's go ahead and throw some numbers in here. 100 volts, I'm going to say I've got 5 ohms. So if I've got 100 volts and 5 ohms, Ohm's law is going to tell me that I equals E over R, And in this case, that's 100 divided by 5 is 20 amps. I have 20 amps of current flowing in this particular circuit, right? It's flowing through that resistor and returning and just doing a big circle. It's being pushed along by this. Push, push, push. Keeps flowing forever and ever. So if I have 20 amps here, let's figure the power on this secondary side. So power equals I times E, right? And my I we just decided is 20 amps. And my E we know is 100 volts. And so that's going to equal 2,000 watts. I'm going to stick in watts because I threw a resistor up there. I'm not going to go back to VA for a while. So I've got 2,000 watts of power there. Or maybe I should, let's go VA. Change my mind, VA. Because what do I got on this side? If I want to decide the power on this side, I've got a coil, right? So let's just think about the power in terms of VA, volts times amps, volt amps, which is my hypotenuse on my power triangle. It's all of the current. We don't care how much is resistive and how much is reactive at this point. We're just figuring out my total current. So over here, P still equals I times E. And over here, I don't know what my current is yet. But I know what my voltage is. So what's my voltage? My voltage is 200 volts. Now what did I say first thing? What's the first rule of transformers? Well, it is that power in equals power out. So I already know what my power is. My power is 2,000 watts. And I know that because whatever power I'm dissipating here has to be the same as the power here. I've stepped the voltage down, so what happens to my current if watt stays the same? Well, let's figure it out. Let's solve this a different way. Let's say I'm going to solve for my current. Well, I equals, let's see, P over E, right? From my Watt's law pie chart, P, I, E, I equals P over E. So in this case, I know what my power is, 2,000 watts, because power is the same here as it is here. Power in equals power out. Now in the real world, you're going to have a little bit of losses at the transformer due to the resistivity of the wires and such. And you can find that labeled as what the Z, what the impedance is of a transformer. And you'll use that later when you have to figure out what the available current is, the available fault current at the secondary of a transformer, which is a thing you'll need to know as an electrician how to do in another class. But having this knowledge will help you get there. So this perfect transformer, power in and power out, are going to equal each other exactly without those losses inherent in a coil. So P over E is 2,000 divided by, my E is 200 volts. 2,000 divided by 200 is 10 amps. So check it out. The turns ratio is 2 to 1. The voltage ratio is 2 to 1. I have twice the voltage here that I have here. I have twice the turns that I have here. But I only have half the current that I have here. In order for this 2,000 watts, or VA, more accurate because I've got a coil, 2,000 VA to be the same on each side, which it has to be by the laws of how these things work, by the second law of thermodynamics. 2,000 VA equals 2,000 VA. The only way for that to happen and voltage to drop is for current to go up. And in fact, current will go up exactly inverse of how voltage is dropped. So in this case, I've got a 2-to-1 voltage ratio. My current ratio is 1-to-2. Now, whenever we talk about a transformer, we always talk about its turns ratio as its voltage ratio. So you're never going to call a transformer a 1-to-2 current ratio. You're going to always talk about its voltage ratio and such, but it's good to understand and know that the current ratio is exactly inverse of the voltage ratio. If my voltage goes down, my current will go up. The amount of current that's actually in this will go up, and also the amount of current that it can supply. So those are the basics on this. We can do some exercises really quick, the sort that I may ask you guys to do in class on these transformers. Let's go ahead and erase this. And I'll throw another transformer up on the board and I'll give some numbers. And I'm doing this by the seat of my pants, so bear with me. This is one of those classes that's really better interactive because I get a lot of questions and we go off on tangents and we talk about different things and we cover stuff. So I just have to think myself about what you guys might be asking. So let's say, again, I've got a source here, whatever it is. And let's say that it's 2,400 volts, AC, 60 hertz. And it's going to a big power transformer. And then over here, I've got a smaller secondary that feeds some sort of load. Now, I'm modeling that load as a resistor. In the real world, that load, this resistor, is going to be your service, right? And everything that's happening on that service. So let's real quickly, let's say that I've got 2,400 volts there. I want a 240 volt system here that I'm going to use as my residential power. I'm going to go ahead and put 240 volts in a panel, center tap the secondary, which the utility does for us to make a ground and a neutral. But essentially, at the nuts and bolts of it, I want 240 volts there. And let's say I've got a service that I'm running on a house or two. Let's say it's a big house. And I've done my load calc, and I need to have 320 amps of current running in that thing. Now I could do the calculation and figure out what my resistor is. And let's do it, what the heck. R equals what? E over I, is that right? Yeah. 240 volts divided by 320, and it's going to be something less than an amp, or excuse me, less than an ohm. And it's interesting when you do that, when you get bigger and bigger loads, the resistance goes down and down. So 240 volts divided by 320 amps, and I got 0.75 ohms. So taking my whole house together, like if I pulled power on my whole entire house and I turned everything on the switch, actually nothing would turn on, but I've got all the switches on, so all of the loads and everything except the electronics that won't turn on without power or won't actually connect without power. And then I put my ohm meter on right across the two lugs of the panel, I might read something close to 0.75 ohms, right? It's not a lot of resistance because I'm going to have a lot of, especially if all 320 amps are flowing. I better have the furnace going with all of its heat strips going too, if I've calculated 320. So anyways, you're probably not actually going to be able to do that calculation because this, when we calculate the service calcs using chapter 220, there are a whole lot of things that we take into consideration that may not actually be happening on the ground as you're actually connecting circuits. The load calculations have a whole lot of D-rates and things in them. I'm going on a tangent now. Going back to this guy. So I've got this 2,400 volt primary coming in and I want 240 volts. Well, what's the difference between 2,400 and 240? Well, that's just a division problem. Most of you can probably do that in your head, right? But let's see, if it's 2,400 divided by 240, that's going to give me, let's see, 1/10, right? So, excuse me, 10 over 1. 2,400 divided by 240 is going to be 10 parts. 10 over 1. So I've got a 10-to-1 step-down transformer. For every 10 volts here, I get 1 volt here. But now how's that 320 amps going to affect the actual current on my primary of this guy? How's this going to see that current? Well, it's going to do the opposite. My 320 amps here, stepping down to 240 volts over here, my 320 amps is going to see a lot less over here. So the current from here to here is going to step way up if I'm going left to right. But if I'm thinking about how's my 320 react to this, well, it's only going to be 1/10 of that. Let's try it and then we'll check it with our math. So what's 1/10 of 320? Well, that's 32 amps. So let's really quickly check power and make sure that that actually worked out right. So P equals I times E, right? And so 32 times 2400, I can't do that in my head. 32 times 2400 equals 76,800 VA. Over here, I've got 240 times 320, 76,800. So, we did that correctly. From left to right, my current steps up. This guy can supply up to 320 amps of current if somehow this was limited at 32 amps, which probably isn't, right? Probably could source a lot more than 32 amps. But the 32 amps I see here is going to be reflected by 320 amps here. The 2,400 volts here is going to step down to 240 volts. So the two are going in opposite directions, if you can see that. Now if I think about it as, well, my voltage steps down to get here, and whatever current it has steps down this direction because I'm coming back, that's a fine way to look at it too. It's all, as long as you understand that if I'm stepping up the voltage this way, I'm stepping down the current this way. If I'm stepping down the voltage this way, which is usually what we do, because we usually have big power transformers that are taking the big utility voltage and turning it into something we can use, then my current is going to be much smaller on the primary than it is on the secondary. I'm going to have more current on the secondary. So as a result, this wire on the big primary transformer can be smaller than this wire, theoretically. Which is kind of crazy to think about. My primary, I think, well, that's the big power, that's where the big voltage is. Well, we don't size our wire by voltage. We size our wire by the current it takes. We size the insulation on our wire by voltage. So this may, in fact, need something. If it's got 2,400 volts, you're not going to put 600 volt rated insulated wire in this, right? It's the utility, you're going to use something bigger. They're going to use that medium voltage cable or something that's got a lot more insulation on it. But the actual size of the conductor, theoretically, can be smaller here than here. And in fact, that's why we use AC, alternating current, and not DC. Because where I generate the power, if you watch the video I asked you to watch, the one that's produced and has the British guy that can't pronounce his THs, if you watch that, you understand that the power that I produce at the turbine, at the power plant, at the nuclear power plant, at the hydroelectric dam, I'm going to produce the biggest voltage I can, or I'm going to even step it up. I'm going to have a similar transformer to this that's going to take the voltage I produce at the hydroelectric dam, and I'm going to step it up to some huge voltage, maybe 12 million volts or some crazy number like that, like you see in the big high tension wires. High tension is just European for high voltage. Tension and voltage are cognates in that way. High tension wires, it's not that they've stretched the wire really high, it's that they've put a bunch of voltage on. Those wires carry a ton of voltage because if they're carrying big voltage, I can carry power somewhere else at a smaller current. And I size my wire for the current. So I can use a smaller wire to do it. I also have the added effect of, as my voltage gets higher, my loss doesn't increase any. It's when my current goes higher that my I square R losses, if I take current squared times the resistance of the wire, that'll give me what my actual loss is over a distance. That gets smaller and smaller. So I can transfer a whole lot more power on much smaller wire and with much less voltage loss, much less power loss due to the resistance of the wire by stepping the voltage way up, and I can send it long distances, which allows us to get our power from the Boardman coal plant in Portland, and get our power from the big hydroelectric dam in the gorge. So that's why we do this, and that's one of the reasons that Edison lost the debate with Westinghouse about whether they should use AC or DC. Edison was so wrapped around the axle about he wanted his system to be used that he said this is an inherently dangerous system because you can electrocute people with it. Well, you can electrocute somebody with DC too. It's just it's a different source of power. So that's about it for transformers. I mean, there's a whole lot more to know. There are lots of different kinds of transformers, and you should take a look at all of them in the book. I'm not going to test on that. I'm going to test you on the stuff here that I've showed you. I'm going to give you a transformer diagram and ask you to solve it. It'll be something that's really easily solvable if you understand that this N ratio, numbers ratio, turns ratio, is the ratio of the primary to secondary in a step down. Now, if I gave you an N ratio that was something different, let's do a different one. If I gave you an N ratio that was 17 to 170. I'm just making numbers up, right? So that's a step up. So if I draw my source here and I'm putting it on there, and I have 17 coils here, and then my secondary has 170, which I'm not going to draw all 170 of them, right, to some power supply. This could be something that the transformer that runs a doorbell is going to be 16 or 24 volts, right? Because what's my voltage going to be here? Say if this is 120 volts AC, 60 hertz, what's my voltage going to be here? Well, 17 to 170, that is a step up. Okay, so I'm doing this wrong already. I was doing a step down. 17 to 170. Let's say I've got, let's call it 100 volts. Let's see what happens, right? I got 100 volts there, 17 to 170. 170 is 10 times as big as 17. So that's the same as a 1 to 10 step up transformer. So whatever I put here, 100 volts, I'm actually going to have 1,000 volts here. But let's say this 100 volt transformer can only supply 20 amps. Maybe it's got an OCPD or a fuse, right? 20 amp OCPD, maybe it's just not going to work over that for whatever reason, however this guy is sourced. It can do 100 volts at 20 amps. So its power is going to be 100 times 20, right? Volts times amps. And that's going to be 2,000 watts. So this guy's going to be maxed at 1,000 volts, 2,000 watts. So therefore, what's its current going to be limited to? Well, I equals P over E, right? And that equals 2,000 over 1,000, 2 amps. So the most I'm going to be able to get is 2 amps out of that. So the biggest load that I can have is something that draws 2 amps. Now, we wouldn't normally size it this way, but just for grins, I've drawn a resistor in there. What's the resistance of that? What's the resistance of that resistor going to have to be at least? Because it could be more resistance and draw less current, right? But there's some number this resistor has to be at least, because if it's smaller than that, this guy's going to try and drive too much current, and it's going to either pop, it's going to pop this OCPD or something, because this guy's going to then try and draw more current. So let's see. If my R by Ohm's law equals E over I, right? And my E in this case is 1,000, and my I is 2. So 2 out of 1,000 is 500 ohms. So that's the smallest that resistor could be, or that's the smallest resistance that resistor could be, is 500 ohms. If this resistor is less than 500 ohms, this guy's going to draw more than 2 amps. And if this guy draws more than 2 amps, this guy's going to draw more than 20 amps. If this guy draws more than 20 amps, it pops out OCPD or fails in whatever way it fails. So that's interesting to note. The one I started to do, but I'd drawn it the wrong way, was talking about like a doorbell transformer or a garage door opener transformer or one of those sorts of transformers that